everyone, and welcome to the Joy of Abstraction Book Club, Chapter 9. We've made it to the interlude, which is really exciting. Things are definitely going to start hotting up after the interlude. The interlude has chapters which are, some of them are quite short, so I hope that you feel like you either have time to catch up where we are every week, or maybe even get ahead, because some of the chapters after the interlude are definitely longer, and I'm thinking about whether we might need more than a week for any of the future chapters. So if you feel strongly that some chapter is going to take you longer than that, or indeed if you get there and discover it's taking you longer, I'm definitely open to questions of the form, please can we have another week on this chapter, because that might help everybody. Anyway, we have some really good meaty questions this time, and by meaty I mean, well, that there's a lot to get our teeth into. I suppose, oh dear, I'm going to get myself caught up in sort of some kind of vegetarianism angst now. Like, why do we call it meaty? Why don't we call it vegetably? Because actually vegetables take more chewing. Oh my goodness, I should have eaten lunch before starting this book club. First question, is there maybe a compiled list somewhere of all the known or commonly used categories? Question. I mean, my instinctive answer is that who's to say what really counts as all the categories? And one of the great powerful things about category theory is that there are so many possible categories that we couldn't possibly list them all. Really, I feel very short. I'm going to just angle my screen down a little bit so that I can pretend to be taller. Commonly used categories, I suppose that it just keeps growing all the time, the categories that people are using. I did try Googling examples of categories. That wasn't very helpful because they weren't mathematical categories. So then I added mathematics to the Google term. And there are some really great blog posts and internet resources where you can see some lists of categories. Most of them will be mathematical examples, probably. But that could help. Some of the classic resources for category theory, I mean, there is the NCAT lab, which is geared towards N categories, but it has a lot of basic category theory on it as well. Wikipedia really isn't bad, but apart from that, there isn't one definitive source on it, because who would pick what would count as the one definitive source? And I think in the end that's a good thing, because there shouldn't be one definitive source. It's a group effort, and between us we can all find many examples. And there was another question about that, further introductory resources. I think there are a lot of good blogs and, well, the internet. That's it. Okay. So someone says, can an object in a category have multiple distinct identity arrows? Would that be useful? I don't think I can imagine an example where it would make sense, yet I find it somehow tempting. That's great, because probably at higher dimensions it is possible, but at the dimension that we're in at the moment, there is indeed only one possible identity arrow on any given object. And it's possible I should have said that in the book somewhere, so thank you for asking that. The proof is a lot like the proof that identities in other places are unique. And it's a good proof as an example of how we prove uniqueness generally in category theory, because what we usually do is we assume that there are two and show that they have to be the same. And so I think I'll just do that now. Let me share the whiteboard screen. Let A be an object of a category C. And suppose we've got two arrows that behave like the identity. So we've got an arrow from A to A that I'll call I, and another one from A to A that I'll call J, both acting as identities. So I'm not going to write out all that it means to act as an identity, but I'll say out loud what it means is that if you compose on either side with another morphism, the result is that that other morphism doesn't change. Okay, so that's what it means to behave as an identity. Well, then in that case, we can compose I with J, right? And because I is an identity, that shouldn't change J. So then what we do, this is typical of this kind of thing. We suppose that there are two things that we're interested in, and then we use the fact that one of them has those properties, and then we use the fact that the other of them has those properties, and then that somehow shows that both of them have to be the same. So we can go, since I is an identity, we know that if we compose it with anything, that thing doesn't change. So in particular, I can compose it with J, and J shouldn't change. So that should equal J, right? But also J is an identity. And so we know that if we compose J with anything, that thing shouldn't change. So now I'm using the fact that J is an identity, so I doesn't change. Therefore, we've shown that I equals J, which is how we show that both those things are equal. Now, if you look at this proof carefully, you'll notice a couple of things. Well, you might notice a couple of things. One is that we only used one side of the identity in each case. So in fact, we have that if one thing is an identity on one side and the other is an identity on the other side, then they have to be the same. So the other thing is that this depended on the fact that there are unique composites for things. So if we ended up in a situation where there weren't unique composites, then we wouldn't get that there were unique identities either necessarily. And that is something that can happen in higher dimensions. In higher dimensional situations, there are morphisms between morphisms. So you can say something sensible about the possibility that there can be different possible composites of the same arrows. They shouldn't be too different. There should probably be an isomorphism between them, in which case you could get different identities for the same thing, but there should also be an isomorphism in between those, so they wouldn't be really, really different. And so that's an example where higher dimensional situations give us a bit more nuance, but as long as we keep enough sensible behavior, so we don't want two things to count as composites that are wildly different from each other, then we will get fairly sensible behavior on the identities. And in higher dimensions, uniqueness takes on different properties. So we don't say given two things, they have to be equal, right? Higher dimensional uniqueness says given two things, they have to be isomorphic. And so then we get to use that higher dimensional uniqueness instead of the low dimensional uniqueness. And then we get just more nuanced situations. So that will come back way towards the end of the book and is much further up the line, as it were. But this, at this level, this is how we prove that identities are unique. And later on, we'll see that we can also prove that inverses are unique like this. And this is when we do universal properties, we'll be doing a lot of uniqueness like this, where we prove that something is unique by saying, suppose there are two, but they have to be the same. Okay, let's go back to the big screen. Next question. Page 112, I talk about the identity arrow being a trivial symmetry. And there's another question about trivial symmetries. Could we say that a 0-degree rotation is different from a 360-degree rotation? And so someone is hoping to learn more about the notion of triviality and in what ways might the notion be helpful? That's a very open question. So I'm not quite sure how much to put into it, because probably one could write a whole book on such a thing. Trivial situations are crucial to think about, because if we didn't, then some of our structure would go away. You know, if we didn't count doing nothing as doing a thing, then we might run into some trouble when just thinking about what we're doing at any given moment. It's like one of my favorite trivial things, which is when things are, you can see I'm starting to get amused even thinking about it, when things are vacuously satisfied. Conditions are vacuously satisfied if there just aren't any things that have to satisfy them. And some of my students tell me that this is their favorite thing they remember about me in a lecture course, saying that there are no elephants in the room and all of them are purple. or something like that. And so that's something being vacuously satisfied, or kind of trivially, but vacuously is a more specific term for it. All the elephants in the room are purple because there aren't any. And so this is very quickly satisfied. So those situations are often of slightly maybe wry or amused interest to abstract mathematicians, because they are extreme cases, and maybe they are some sort of initial object, and that's something we'll see later. But they're definitely the cases that you might overlook. You might overlook them because they're so trivial, but then they can get in the way if you do overlook them. And actually, I was talking to a math friend the other day who said that they once played 20 questions with another math friend, and I hope they don't mind me telling this story, but they got really confused because all the answers seemed to be contradicting each other. They worked out that it was some kind of collection of people. Did all the people do the same thing? Yes. Did all the people do different things? Yes. Their answer turned out to be the empty set, which I thought was very funny. And all the mathematicians present also thought it was very funny. Perhaps the non-mathematicians, any non-mathematicians present would have found it really annoying. But I find it funny. So as for a 0-degree rotation versus a 360-degree rotation, we could certainly think of a world where those two things did want to count as different. But in that case, the 360-degree one probably wouldn't count as an identity anymore. It would just count as a transformation that is different. And in a way, that's what happens if you draw a graph of sine, right? If you draw a graph of a sine wave, you have to go past a 360-degree rotation or a full rotation, because it keeps going, and then the sine wave starts repeating itself, but you are thinking about having gone more than 360 degrees around. Could an identity via reflection be different from an identity via rotation? If you were going to count a 360-degree rotation as different from the identity, I suspect that the identity via rotation could not be different from the identity via reflection, because the identity, there isn't really an identity via reflection. So you can rotate something by 0 degrees, but a reflection has to be performed through a line or through a point. And if you consider just reflections, then there isn't one that leaves everything in the same place, because it has to go through a line. And so let me think about this. Let me think about this for a second. You can consider just the rotations in a situation, and you will get a sensible situation because you can do rotation by 0. If you just consider the reflections, you will not get a sensible situation, which is to say you won't get a group because you won't have an identity. So for example, if I think about all the reflections on this rectangle, there are 2 of them. There's reflection this way and there's reflection that way, but then there's no identity reflection. So I think the answer is that there isn't an identity reflection. Okay, so there are now a couple of questions about the expression of an equivalence relation as a category. So one question says, can we define an equivalence relation as a category that has at most 1 arrow between objects and where there are inverses for every arrow? And the answer to that is yes. You have to be a bit careful. And this is something I always have to sit down and think about for ages, because it's not given, you have to be careful, because you say, given a pair of objects A and B, there is at most 1 arrow from A to B. You don't say that there is at most 1 arrow between the objects A and B. And that the notation, the terminology is horrible, I apologize, but one of those is a pre-order and one of them is a partial order. So in a partial order, you say that there is at most 1 arrow between A and B, which means that if you have one going from A to B, you can't have a different one going from B to A. So the only way you can have an invertible arrow in a partial order is if it's an identity. So that means there are no non-trivial isomorphisms. Whereas for a pre-order, you can have an arrow from A to B and another arrow from B to A. Perhaps I should write this down because it's really confusing. I duly get confused every time I have to think about it. In a pre-order, and I did just look this up, so I hope I'm getting it right. Given objects A and B, that doesn't look like there, does it? There is at most one arrow from A to B. But there could be another B to A. Whereas in a partial order, given objects A and B, there is at most one arrow between A and B. So this is equivalent to the anti-symmetry condition, which says that if A is less than or equal to B and B is less than or equal to A, then they have to be equal. So this produces anti-symmetry if A kickboards B and B kickboards A, as we had in the previous video, this term kickboard for the little relation sign, then A has to equal B. And that's why it makes sense to think of these as less than or equal to, because what it's like saying if A is less than or equal to B and B is less than or equal to C, then there's no choice but they have to be equal. Whereas in this situation, you can have them being non-trivially isomorphic. So we can have, and I guess we haven't done isomorphism yet, but it means that we can have a relationship between A and B that goes both ways, even though A and B aren't the same. Whereas in a partial order, you can't have that. And so for an equivalence relation, we really want to be able to have this, because otherwise, because in an equivalence relation, it's symmetric. And so you always have, whenever A is related to B, B is related to A. But if we also had anti-symmetry, then we would get that whenever A is related to B, then A equals B. So nothing would be related to anything other than itself. So that would be a bit uninteresting. So it's very important that we do the partial order version when we're doing equivalence relations. But then in that case, yes, an equivalence relation is exactly a category in which, given any objects A and B, there's at most one arrow A to B, and every arrow has an inverse. That is an arrow going back again. I suspect I didn't call it an inverse necessarily in that chapter because we haven't really done inverses yet. But then the next question says, does a categorical description of a mathematical structure uniquely identify that structure? And the question is, it depends how you've done it and how well you do it. And so let me just go back to the full screen. The idea of expressing a structure as a category is to pin it down exactly so that you can actually define it to be like that. But sometimes you're just characterizing it in order to show that there are things you can do. And so I don't think that there is a global answer to this question. I think it depends, but the most preferable situation is where you have entirely pinned it down. What we will see is that there is something more subtle to say about it, which is that what we really want to pin down is the totality of those structures. So we might want to say, for example, another example is about monoids and categories. And if you don't know what these mean, it doesn't matter at the moment. It's just to give the general flavor of the example. You can say that a monoid is exactly a category with one object, but then there's a little subtlety going on. And so it's better to say that the category of monoids is somehow related to the category of categories with one object, because we're doing category theory, right? So what we're really interested in is a whole collection of structures and their relationships between them, not just the individual structures. That's a bit of a subtle point, though. So now there are a few questions about my distinction between data, structure, and properties. And perhaps I should have made this more clear in the book, that that distinction is really it's more of a helpful way of thinking that I have found to help. That's why it's helpful, rather than something technical. And so I think this is definitely one of the problems with learning math, that it's not always clear which things are technical definitions and which things are people saying things to help themselves. And this is definitely me saying things to help myself. And I had a little look around the internet and found that some other people don't distinguish between data and structure. I distinguish between data and structure because I find that helpful, and because I think that data is basic building blocks and structure is things that you do with them, and properties are then sort of rules that those things satisfy. And so someone asked about the table at the bottom of page 113 and the fact that the bottom left is blank. And so what this is, it's this table here. And what this is saying is it's giving a point of view on what plays what role in an equivalence relation and a category. And this question says, does a categorified equivalence relation? Okay, so I'm going to stop right there. And I think I know what you mean by saying categorified, because what we're doing is expressing an equivalence relation in category theory. But in category theory, that's not what categorified means. In category theory, categorified means adding an extra dimension to things in order to weaken the situation. So this is not a categorification of an equivalence relation. It is just expressing an equivalence relation in terms of a category. And the reason that I've left the bottom left-hand side blank is that there's been a shift in dimension, and a category has a lot more possible stuff going on than an equivalence relation. The fact that that bottom left-hand corner is blank is really a sign that an equivalence relation is a much less expressive kind of structure, which is why you just don't have anything in that bottom left-hand place, because everything has already been expressed. By the time you get to the level of structure in a category, everything has already been expressed. And so the fact that the properties of an equivalence relation are expressed as structure in a category shows that a category is kind of it's a richer place, I think. And the fact that the relations of an equivalence relation count as structure there, but count as data in a category, show that in a category, we're leaving more room for more things to happen, because the structure is expressed as arrows and those count as basic building blocks. They really are more, they just have more space for more possible expression. So the next person asks what the difference is between properties and structure. So properties are definitely rules. They're things that are true or false about a situation. And so if something either has a property or it hasn't, whereas a piece of structure is something you can add to a situation. A property is something that just is or isn't true. And I think that's what the difference is for me. I think that it's hard to say, because it depends on context. And this person says, this led me to believe that structure is an alternate term for properties in the context of category theory. And no, I don't think it's that. I think it's that, okay, let me look at this diagram again. So when you're in an equivalence relation, the relations are things that are either, the relations are things that are, okay, hold on a minute. Let me pause and get my wording right. Okay, I think what I'm trying to say is that the way you usually express an equivalence relation is that you start with a set of things that you're studying, and then you say that you're going to study this particular equivalence relation on that set, which is why the equivalence relation feels like some extra structure that you're putting on that set. Whereas abstractly in a category, the data that you start with is objects and morphisms, and you say, now I'm going to consider the following category structure on that. It's definitely not a formally defined situation, which is why the difference between data and structure is, I think, a little bit hazy. I think that the difference between structure and properties is clearer cut, because properties are things that are true or false. And that the properties are things you're requiring to be true, whereas structure is stuff that you're imposing. Now, I think when we do forgetful functors, it becomes a bit clearer as a point of view, because a forgetful functor forgets some of the things. And what's really going on maybe is that it's a question about how far you can forget and sort of get back to the stuff that you started with. And so if you start with a category and you forget the arrows, you sort of don't know what you're doing anymore. It doesn't bear any resemblance to the category that you originally had. Whereas if you start with a set with an equivalence relation and you forget the equivalence relation, you've still got the set that you were originally thinking about. So I hope that helps a bit. It's definitely, because it's something a bit ideological and it's a point of view, it's, I guess, something I can't pin down properly. One might argue that if I can't pin it down properly, then I don't really understand it myself. And maybe that's true, I don't know, but it is something that I find helpful as a point of view. I suppose I could just come up with a lot of other examples of things where there are things that count as data, things that count as structure, and things that count as properties. And some of these might be things that you haven't heard of, so it might not help at all. But for example, a group is a set equipped with a binary operation and an identity. So the binary operation and the identity are definitely pieces of extra structure on the underlying data, which is a set. And then you ask that the binary operation and the identities satisfy some properties. Oh, I forgot the inverses. So a metric space is a set of points equipped with a metric, and then the metric satisfies some properties. So it's clear to me that that is data, structure, and properties. Yeah, I think that's all I'm going to say about that. Oh, and someone finally says, data seems to refer to the things we have to play with. Properties seem to refer to constraints. Structure is a bit more ambiguous. Yeah, so I suppose data is the things we have to play with. Structure is kind of the ways we get to play with them. And then properties is kind of the rules. So if it were a game, data is like the pieces that we're using. Structure is like the moves we can do. And properties is like the rules of the game. Yeah. Okay, the next question. Not all categories have inverses. That is, not every morphism in a category has an inverse. An inverse is an arrow going backwards that invert the original morphism, according to the definition in chapter 8. However, in chapter 9, we see that all categories have a dual category. That's right, where you just consider all the arrows to be going backwards. it seems that although we don't necessarily expect to see any inverse arrows within a category, a pulled out look at category theory will always find some inverse arrows. Now we have to be careful because when we take the dual category, we're not actually taking inverse arrows at all. We're just considering the morphisms to be going the other way. Hopefully this will become clearer in the chapter on duals. So then this question says, does this mean the category of category has inverses? And the answer is no, because duals aren't about mapping between categories in different directions. They're about just taking a category and considering the arrows to be going in a different direction, which gives us a dual category, but it doesn't give us inverse morphisms. So let me share the whiteboard screen again. Given a category A, given a category C, there is always a dual category called C op. But that's nothing to do with inverses in the category of categories. It's just an object, another object in the category that happens to be related. So this has nothing to do with inverses, in fact. Page 114, the text asks us to remember that a diagram commutes if all paths through it between the same endpoints are the same. Have I understood correctly that not all diagrams in a category commute? That is correct. And that's one of the powerful things about categories, that to look at when diagrams commute and when they don't commute. The examples so far have, I think that's because we've been looking at a lot of categories in which there is at most one morphism from any object to any other. And in those categories, everything always commutes because there is only one possible morphism from any A to any B. Yes, there could be some that don't, and yes, there could be diagrams where parts of them commute and parts of them don't. So, for example, in the category of sets and functions, we haven't really done the category of sets and functions yet, but in the category of sets and functions, there are loads of different functions. There are many different possible functions from anything to anything else. And so if you just look at the function from the set containing the number 1 to the set containing the numbers 2 and 3, then there are two possible different functions, one of them which produces the number 2 and one of them produces the number 3. So we could call that adding 1 and we could call it adding 2. It doesn't really matter what we call it. The point is that in one of them, 1 lands on the number 2 and the other one lands on the number 3. And so we could make a diagram that doesn't commute out of this. So we're going, everything is a one element set apart from this last one. So this top function is going to add 1. So it takes us to 2. This bottom function is going to add 2. I mean, that is the only possible function here and the only possible function here. And then this function is going to just take 2 to exactly where it goes. So that's going to be kind of do nothing. And this one is also going to do nothing. So if we go around this way, then the number 1 is going to land on the number 2. And if we go around this way, the number 1 is going to land on the number 3. So this diagram does not commute. In fact, this diagram already didn't commute. It's just a bit weirder to think about a diagram with only 2 parallel arrows commuting or not commuting. Because if you've just got 2 parallel arrows, commuting means the arrows are the same, and not commuting means the arrows aren't the same. So this one already doesn't commute. It's just this one looks more like a square, and so maybe it's it's clearer to see it in that context that it doesn't commute. Page 115. There's a question saying, I'm wondering which properties of number systems are being assumed as axioms and which are being demonstrated categorically. In that particular example, I believe all I was doing was using less than or equals for numbers. So not very much was being assumed at all. All that was being assumed was that there is an ordering on a total ordering on the numbers. And page 116, if we turn all the arrows around but leave everything else the same, it's the dual category. It hasn't really changed the structure, it's just presented differently. How does this connect to thinking about the difference between product and co-product? Well, we haven't come to product and co-product yet, and that comes much later, but that is the entire point of products and co-products. The co-product is the dual of the product. I'm honestly quite curious how you have possibly met products and co-products without having met the fact that those are dual to each other. Is there some resource somewhere that says what products and co-products are without saying that they are dual to each other? That is something I find slightly alarming as a concept, because that's kind of the whole point about them. Anyway, that's the end of the questions for today. Some appreciation. These examples are extremely helpful for upcoming definitions. Thank you for including them early on. You're welcome. Thanks for writing the book and for taking time to allow us to ask questions. I'm enjoying following along. You're very welcome. Thanks for all the work in running the book club. Thanks in advance. Thank you. Thank you. Well, thank you all. I think that the next chapter is really short, so perhaps there won't be very many questions, but perhaps there'll be some really meaty, I was about to say meaty again and end up where we started. Perhaps there'll be some really tasty, substantial questions. If it's a very short one, then that's fine. And I hope that you all have a lovely week. See you next time. And thanks again to the Topos Institute for hosting. Bye.